Synchronous versus asynchronous replication. An important detail of a replicated system is whether the replication happens synchronously or asynchronously. In relational databases, this is often a configurable option. Other systems are often hard-coded to be either one or the other. Think about what happens in Figure 5-1, where the user of a website updates their profile image. At some point in time, the client sends the update request to the leader. Shortly afterward, it is received by the leader. At some point, the leader forwards the data change to the followers. Eventually, the leader notifies the client that the update was successful. Figure 5-2. Leader-based replication with one synchronous and one asynchronous fall lower. In the example of Figure 5-2, the replication to follower 1 is synchronous. The leader waits until follower 1 has confirmed that it received the write before reporting success to the user, and before making the write visible to other clients. The replication to follower 2 is asynchronous. The leader sends the message, but doesn't wait for a response from the follower. The diagram shows that there is a substantial delay before follower 2 processes the message. Normally, replication is quite fast. Most database systems apply changes to followers in less than a second. However, there is no guarantee of how long it might take. There are circumstances when followers might fall behind the leader by several minutes or more. For example, if a follower is recovering from a failure, if the system is operating near maximum capacity, or if there are network problems between the nodes. The advantage of synchronous replication is that the follower is guaranteed to have an up-to-date copy of the data that is consistent with the leader. If the leader suddenly fails, we can be sure that the data is still available on the follower. The disadvantage is that if the synchronous follower doesn't respond because it has crashed, or there is a network fault, or for any other reason, the write cannot be processed. The leader must block all writes and wait until the synchronous replica is available again. For that reason, it is impractical for all followers to be synchronous. Any one node outage would cause the whole system to grind to a halt. In practice, if you enable synchronous replication on a database, it usually means that one of the followers is synchronous and the others are synchronous. If the synchronous follower becomes unavailable or slow, one of the asynchronous followers is made synchronous. This guarantees that you have an up-to-date copy of the data on at least 2 nodes, the leader and one synchronous follower. This configuration is sometimes also called semi-synchronous. Often, leader-based replication is configured to be completely asynchronous. In this case, if the leader fails and is not recoverable, any writes that have not yet been replicated to followers are lost. This means that a write is not guaranteed to be durable, even if it has been confirmed to the client. However, a fully asynchronous configuration has the advantage that the leader can continue processing writes, even if all of its followers have fallen behind. Weakening durability may sound like a bad trade-off, but asynchronous replication is nevertheless widely used, especially if there are many followers or if they are geographically distributed. We will return to this issue in Problems with Replication Lag on page 161. Research on replication. It can be a serious problem for asynchronously replicated systems to lose data if the leader fails, so researchers have continued investigating replication methods that do not lose data but still provide good performance and availability. For example, chain replication is a variant of synchronous replication that has been successfully implemented in a few systems such as Microsoft Azure Storage. There is a strong connection between consistency of replication and consensus getting several nodes to agree on a value, and we will explore this area of theory in more detail in Chapter 9. In this chapter we will concentrate on the simpler forms of replication that are most commonly used in databases in practice. Setting up new followers. From time to time, you need to set up new followers, perhaps to increase the number of replicas or to replace failed nodes. How do you ensure that the new follower has an accurate copy of the leader's data? Simply copying data files from one node to another is typically not sufficient. Clients are constantly writing to the database, and the data is always in flux, so a standard file copy would see different parts of the database at different points in time. The result might not make any sense. You could make the files on disk consistent by locking the database, making it unavailable for writes, but that would go against our goal of high availability. Fortunately, setting up a follower can usually be done without downtime. Conceptually, the process looks like this. Take a consistent snapshot of the leader's database at some point in time if possible, without taking a lock on the entire database. Most databases have this feature, as it is also required for backups. In some cases, third-party tools are needed, such as in OBQPX for MySQL. Copy the snapshot to the new follower node. The follower connects to the leader and requests all the data changes that have happened since the snapshot was taken. This requires that the snapshot is associated with an exact position in the leader's replication log. That position has various names. For example, PostgreSQL calls it the log sequence number, and MySQL calls it the bin log coordinates. When the follower has processed the backlog of data changes since the snapshot, we say it has caught up. It can now continue to process data changes from the leader as they happen. The practical steps of setting up a follower vary significantly by database. In some systems, the process is fully automated, whereas in others it can be a somewhat arcane multi-step workflow that needs to be manually performed by an administrator. Handling node outages. Any node in the system can go down, perhaps unexpectedly due to a fault, but just as likely due to planned maintenance. For example, rebooting a machine to install a kernel security patch. Being able to reboot individual nodes without downtime is a big advantage for operations and maintenance. Thus, our goal is to keep the system as a whole running despite individual node failures, and to keep the impact of a node outage as small as possible. How do you achieve high availability with leader-based replication? On its local disk, each follower keeps a log of the data changes it has received from the leader. If a follower crashes and is restarted, or if the network between the leader and the follower is temporarily interrupted, the follower can recover quite easily. From its log, it knows the last transaction that was processed before the fault occurred. Thus, the follower can connect to the leader and request all the data changes that occurred during the time when the follower was disconnected. When it has applied these changes, it has caught up to the leader and can continue receiving a stream of data changes as before. Handling a failure of the leader is trickier. One of the followers needs to be promoted to be the new leader. Clients need to be reconfigured to send their rights to the new leader, and the other followers need to start consuming data changes from the new leader. This process is called failover. Failover can happen manually. An administrator is notified that the leader has failed and takes the necessary steps to make a new leader, or automatically. An automatic failover process usually consists of the following steps: determining that the leader has failed. There are many things that could potentially go wrong: crashes, power outages, network issues, and more. There is no foolproof way of detecting what has gone wrong, so most systems simply use a timeout. Nodes frequently bounce messages back and forth between each other, and if a node doesn't respond for some period of time, say 30 seconds, it is assumed to be dead. If the leader is deliberately taken down for planned maintenance, this doesn't apply. 2. Choosing a new leader. This could be done through an election process, where the leader is chosen by a majority of the remaining replicas, or a new leader could be appointed by a previously elected controller node. The best candidate for leadership is usually the replica with the most up-to-date data changes from the old leader to minimize any data loss. Getting all the nodes to agree on a new leader is a consensus problem, discussed in detail in Chapter 9. Reconfiguring the system to use the new leader. Clients now need to send their write requests to the new leader. We discussed this in request routing on page 214. If the old leader comes back, it might still believe that it is the leader, not realizing that the other replicas have forced it to step down. The system needs to ensure that the old leader becomes a follower and recognizes the new leader. Failover is fraught with things that can go wrong. If asynchronous replication is used, the new leader may not have received all the rights from the old leader before it failed. If the former leader rejoins the cluster after a new leader has been chosen, what should happen to those rights? The new leader may have received conflicting rights in the meantime. The most common solution is for the old leader's unreplicated rights to simply be discarded, which may violate clients' durability expectations. Discarding rights is especially dangerous if other storage systems outside of the database need to be coordinated with the database contents. For example, in one incident at GitHub, an out-of-date MySQL follower was promoted to leader. The database used an auto-incrementing counter to assign primary keys to new. This approach is known as fencing, or, more emphatically, shoot the other node in the head stunneth. We will discuss fencing in more detail in the leader and the lock on page 301 rows. But because the new leader's counter lagged behind the old leader's, it reused some primary keys that were previously assigned by the old leader. These primary keys were also used in a ready store, so the reuse of primary keys resulted in inconsistency between MySQL and readies, which caused some private data to be disclosed to the wrong users. In certain fault scenarios, see Chapter 8, it could happen that two nodes both believe that they are the leader. This situation is called split brain, and it is dangerous. If both leaders accept rights, and there is no process for resolving conflicts, see multi-leader replication on page 168, data is likely to be lost or corrupted. As a safety catch, some systems have a mechanism to shut down one node if two leaders are detected. Roman 2 However, if this mechanism is not carefully designed, you can end up with both nodes being shut down. What is the right timeout before the leader is declared dead? A longer timeout means a longer time to recovery in the case where the leader fails. However, if the timeout is too short, there could be unnecessary failovers. For example, a temporary low spike could cause a node's response time to increase above the timeout, or a network glitch could cause delayed packets. If the system is already struggling with high load or network problems, an unnecessary failover is likely to make the situation worse, not better. There are no easy solutions to these problems. For this reason, some operations teams prefer to perform failovers manually, even if the software supports automatic failover. These issues, node failures, unreliable networks, and trade-offs around replica consistency, durability, availability, and latency are in fact fundamental problems in distributed systems. In Chapter 8 and Chapter 9 we will discuss them in greater depth.